Let's continue with our topic of semiconductor photodetectors. In the previous lecture, I gave you an introduction to photodetectors. Then we discussed direct and indirect bandgaps photodetectors. Then we talked about semiconductor photodetector parameters, and we discussed some of the semiconductor photodetector types. So in the previous lecture, we mentioned photoconductor, PN photodetector, PIN photodetector, and we also discussed metal semiconductor metal photodetector. In today's lecture, we will discuss Avalanche photodiode, which is the fifth type of photodetector, and then finally we will talk about photodetector noise, which is also a crucial topic related to photodetector. So let us jump to the slide related to Avalanche photodiodes, which is slide number 30. Here is the configuration of Avalanche photodiodes, and it kind of looks similar to the PIN photodetector. Like in the PIN photodetector, we had a P-type region, we had an I layer, and we had an N-type layer. And also, it is supposed to be connected to a load resistor, and it operates under reverse bias, where the positive terminal is connected to the N-type layer, and the negative terminal is connected to the P-type layer. But actually, there are a few distinctions between the Avalanche photodiode and the PIN photodiode. The first difference is in terms of configuration is this small layer which you can see adjacent to the N-type layer, and then we have an I layer, and then we have another P-type layer. We did not have this layer in the PIN photodetector, and there is a significance of this layer which we are going to discuss in a bit. Secondly, Avalanche photodiode operates at relatively high voltages as compared to the PIN photodiode. Like it's supposed to operate at more than 10 volts, which is necessary. The high voltage is necessary for the operation of the Avalanche photodiode. So here, let us look at the configuration once again. In Avalanche photodiodes, this voltage is high enough so that the depletion width is extended throughout the entire layer, throughout the entire I layer of this structure. We know that the depletion width increases with an increase in the reverse bias voltage. So keep increasing the reverse bias voltage. Initially, the depletion width would be extended to this region, and it's going to further increase and increase with an increase in the reverse bias voltage. And there comes a point, if you keep increasing the reverse bias voltage, there comes a point when this depletion width is extended throughout the entire I layer of this structure. And that point is called, the voltage corresponding to that is called the reach through voltage. And since it requires a high reverse bias voltage, it actually gives enough kinetic energy to the electrons in this region to knock off secondary electrons from the atoms in this region. And then these secondary electrons further have energy to knock off more number of electrons from other atoms. This concept is clear in this figure over here as well, where we have high energy electrons. They strike other atoms, resulting in the emission of electrons. And then these secondary electrons, they strike other atoms, have enough kinetic energy, and knock off more number of electrons. So basically, when light is incident on this structure, it's going to result in the generation of an electron hole pair. And then this electron because of the high reverse bias voltage, positive terminal is going to move towards the left. The hole is attracted to move towards the right. This electron in this region gains enough kinetic energy so that it can knock off more number of electrons. So the incident photon, assume the incident photon, in this case we have just assumed one photon, but it results in the generation of multiple electrons, multiple carriers. So it has a multiplication factor. Now let us focus on this configuration. We know here we have an NP region. We know from the concept of the depletion region that inside the I layer adjacent to the metallurgical junction we have uncovered positive charges. Similarly, in the P region adjacent to this metallurgical junction we have uncovered negative charges. In the I layer, we don't have much number of uncovered charges. We just have the electron hole pair generated as a result of these incoming photons. And then we have uncovered charges in this P plus region as well. So because of these uncovered charges, the magnitude of the electric field will start increasing. It pretty much stays the same inside the I layer, and then it's going to be the maximum at this PN junction. So because of this maximum electric field, the knocking off of the electrons occurs in this region. The avalanche process actually occurs in this region. And the terminology avalanche comes from the concept of a kind of, you can assume, a snowball. When a snowball starts rolling down the slope, it gathers more snow with it. With the passage of time, its size keeps increasing. So it's called an avalanche process. Similar to that, with the passage of time, these electrons, they knock off more number of secondary electrons and their number increases. And this process is called the avalanche process. And this photodiode is called the avalanche photodiode. So let us consider this figure in which we have plotted current versus the reverse bias voltage. Initially, at a reverse bias voltage of around 20 volts, looking at the blue curve, we have a particular dark current plus photocurrent, where the photocurrent is a result of the incoming incident photons on the photodetector. Then as we keep increasing the reverse bias voltage, there comes a point where, like for example, assume at around 24 volts, we have a multiplication factor of 1. The multiplication factor is given on the right side. So you have a multiplication factor of 1. It means that for every incident photon results in the generation of one electron hole pair. So this point over here where the multiplication factor is 1 is called the reach through voltage. And as I already discussed, that at the reach through voltage, the depletion region extends throughout the entire I layer of the avalanche photodiode configuration. So at this point, our current is a combination of the dark current plus photocurrent. The dark current is given over here. If we further keep increasing, for example, increase the reverse bias voltage up to 40 volts, we see a multiplication factor of around 5. So at this point, each incident photon results in the generation of 5 electron hole pairs. And then further keep increasing the voltage. At 45 volts, this multiplication factor is more than 10. But there comes a point at which this photocurrent plus dark current starts increasing drastically. And this point is called the breakdown point. It's called the breakdown because now the current is really high, resulting in heating and permanent damage of the device. So we generally like to avoid operating any kind of device in their breakdown region, except for xenodiodes, which we operate in the breakdown region. So consider an avalanche multiplication factor M, which is the ratio of the multiplied photocurrent divided by the primary photocurrent. M is equal to the multiplied photocurrent represented with IPH divided by the primary photocurrent represented with IPHO. This multiplication factor can also be calculated using this formula 1/1 minus VR. VR is the reverse bias voltage, divided by VBR. VBR is the breakdown point of the photodiode, to the power of small n, where n is an empirical fit number. For silicon, its value is approximately 100, and for germanium, its value is approximately 10. Now, let us try to understand a silicon avalanche photodiode with the help of an example. So consider a silicon avalanche photodiode which has a quantum efficiency of 70% at a wavelength of 830 nanometers in the absence of multiplication, that is m is equal to 1. Then the avalanche photodiodes is operate with a multiplication of m is equal to 100. If the incident optical power is 10 nanowatt, what is the photocurrent? So here we have to calculate the photocurrent for two scenarios, for a multiplication factor of 1 and for a multiplication factor of 100. For a multiplication factor of 1, it means the primary photocurrent. We need to calculate the primary photocurrent. We know from the definition of the responsivity that responsivity is equal to the output photocurrent divided by the input optical power. So from this relationship, we can reorder it to calculate the primary photocurrent is equal to responsivity times the input optical power. The input optical power is given, it's 10 nanowatt, but we don't know the responsivity. So let us first calculate the unmultiplied responsivity, equal to efficiency times this equation. We already know about this equation. There is a relationship between responsivity and quantum efficiency. Putting all the values, we know the value of the quantum efficiency. Put in all the values in our responsivity, the unmultiplied responsivity comes out to be 0.47 amps per watt. Replace its value, results in the primary photocurrent or the unmultiplied photocurrent, giving us a value of 4.7 nanoamps. And then from the definition of the multiplication factor, we know that m is equal to the multiplied photocurrent divided by the primary photocurrent. So the multiplied photocurrent is equal to multiplication factor times the primary photocurrent. So here is how you calculate the multiplied photocurrent, equal to multiplication factor is 100 times the primary photocurrent. So multiplied photocurrent comes out to be 470 nanoamps. Here we have another example based on indium gallium arsenide based avalanche photodiodes. Quantum efficiency is given, wavelength of the input incident light is given. Initially we consider absence of multiplication, and then we consider a multiplication factor of 12. The incident optical power is 20 nanowatts. So what is the responsivity when the multiplication factor is 10? So in this example, we have to calculate the primary photocurrent, the unmultiplied photocurrent's responsivity. We have to calculate the multiplied photocurrent, and we have to calculate the multiplied photocurrent's responsivity. So in order to calculate the primary photocurrent, we need responsivity. The unmultiplied photocurrent responsivity equal to this equation turns out to be 0.75 amperes per watt. then our primary photocurrent comes out to be 15 nanoamps. Now, the photocurrent, the multiplied photocurrent is equal to the multiplication factor times the primary photocurrent. So, the multiplied photocurrent is 180 nanoamperes. Now, the responsivity corresponding to the multiplied photocurrent is equal to the multiplied photocurrent divided by the input optical power. Now, the multiplied photocurrent is 180 and the input optical power is 20 nanowatts. So, 180 divided by 20 gives us a responsivity of 9 amperes per watt. Here I have listed different photodetectors for a comparison purpose. For example, we have a silicon PN junction photodetector which has a certain responsivity gain and speed. Then the silicon PIN photodetector has similar characteristics to that of the PN photodetector, but its speed is much higher as compared to the PN junction photodetector, as we discussed in its primary properties, that the PIN photodetectors are generally faster as compared to the PN photodetectors. Then look at the Avalanche photodiode, silicon Avalanche photodiode. Its responsivity is much higher as compared to the responsivity of PIN and PN photodetector, because we have a multiplication factor in Avalanche photodiode, and because of the multiplied photocurrent. And similarly, the gain of silicon Avalanche photodetectors is also much higher as compared to the PN and PIN photodetectors. Similarly, we have other kind of photodetectors, germanium based and indium, gallium arsenide based. Their wavelength range is generally suitable for communications. Now, we have covered the different types of photodetectors, and we are gonna focus now on the noise related to photodetectors. Now, here are the components of a basic photoreceiver, in which we have a photodiode, a load resistor, reverse bias voltage. So the incoming incident photons are going to result in the generation of electron hole pairs, resulting in a photocurrent across this circuitry. But this photocurrent is not enough to be properly detected. So we actually need a pre-amplifier stage in front of this circuitry in order to amplify the signals. The signals they are amplified enough so that they are detected and further processed by data acquisition and processing. There are some key properties, some key requirements for a good photoreceiver. The first is it should have high sensitivity at operating wavelengths. Then it should have good optical to electrical conversion efficiency. It should have fast response times. The speed of the photodetector can be improved by using a suitable configuration. For example, PIN photodetector has a higher speed as compared to a PN photodetector or as compared to a photoconductor. It should have minimum noise. Now, a photodetector should be able to detect low input optical power levels as well, and it can do so if the noise in the photodetectors is low. So we can improve the photodetector in terms of noise if we reduce the dark currents related to the photodetector, and the dark currents can be reduced by growing high quality films based photodetectors. So the growth perspective actually covers this part. the photoreceiver should have high linearity. Linearity actually means that over a particular wavelength range of operation, if the input optical power is increased, the corresponding photo generated current should also increase. So these are some of the basic properties, some of the key properties or key requirements of a good photoreceiver. Photodetector's noise. As already mentioned, that a photodetector should be able to detect low input optical power levels, and it can do so if the noise in the photodetector is low. So it is crucial to keep the noise in the photodetectors low. And the noise can actually come from three sources. It can come from the dark current, which has a statistical nature. It can come from the photocurrent, which also has a statistical nature. And thirdly, the noise can come from the load resistor, which is called thermal noise. The dark current related noise and the photocurrent related noise is called quantum noise or short noise. And the noise related to the load resistor is called thermal noise. Now the signal to noise ratio in a photodetector is equal to the signal power divided by the noise power from the photodiode plus noise power from the amplifier. Short noise in photodetector. As already mentioned, that this photodetector has two kinds of noise. Noise corresponding to the dark current and noise corresponding to the photocurrent. The dark current in itself has statistical nature. If you look at a leakage current of a diode or a photodetector under dark conditions, under a microscope, you would see variations around the mean level of this current. It's not at a constant level. There are certain variations. It has statistical nature. Similarly, the noise related to the photocurrent also has statistical nature, because the incoming incident photons all the incoming incident photons do not hit this surface at the same time. They hit this surface randomly or at different times. And this is not just one photon or a few number of photons. For example, assume that the incoming incident light has a power of 1 microwatt. Now this 1 microwatt power has 1 microwatt divided by h nu, where h is the Planck's constant, nu is the frequency, and nu can also be represented in c divided by lambda form. So it's 1 microwatt divided by h nu number of photons, which turns out to be approximately 7.8 trillion photons that hit the photodiode within each second. 7.8 trillion photons. And these photons do not hit this surface at the same time. They hit them at different times. So the photo-generated carriers are also generated at different times. So the current related to this photo-generated carriers has also statistical nature around a mean point. So here we have plotted a number of incident photons versus times, and these photons would result in the generation of carriers. We will have photo-generated carriers because of these incident photons. The photo-generated carriers are also represented versus time. Now these photo-generated carriers would result in current pulses, and wherever we have more number of generated photo carriers, they will have more number of current pulses. And then if we plot the mean current, we would see variations around of the generated photocurrent around a mean level. The RMS of fluctuations is equal to the square root of the square of this current. So as already discussed that the photodiode has two kind of noises related to it. The one is the current, the noise related to the dark current, and the second one is the noise related to the photocurrent, and both of them have statistical nature. The dark current noise can be represented, it is also called the short noise, with the help of this equation: 2 times charge on electron times the dark current times bandwidth of the photodetector. Bandwidth actually means the frequency range of operation of the photodetector, and this quantity is related to the rise and fall times of the photodetector. The higher the bandwidth, the smaller the rise and fall time of the photodetector, and the higher the speed of the photodetector. So higher bandwidth actually corresponds to higher speed of a photodetector. Similarly, the quantum noise can be represented using this equation: 2 times charge on electrons times the photo generated current times the bandwidth, and we take square root of it. And the total short noise current is the sum of the dark noise current plus photo generated current noise. The signal to noise ratio is equal to the signal power divided by noise power, which is equal to IPS square RL divided by IN square RL, or RL and RL cancel out. So it's equal to IPS square divided by IN square, we already know, is the sum of the dark current plus photo current. The third kind of noise comes from the load resistor, and it's called the thermal noise. And here is a representation for the thermal noise: 4 times Boltzmann constant times temperature times bandwidth of the photodetector divided by the load resistance. Noise equivalent power is the input optical power that generates a photocurrent that is equal to the total noise current, or it represents the required optical power to achieve an SNR of 1 at 1 Hz. What does it mean to achieve an SNR of 1? It means that the signal power is equal to the noise power. So SNR is equal to 1 means the signal power is equal to the noise power, which further means that noise equivalent power is the minimum power required for the operation of a photodetector. So in this case, SNR is equal to 1, which means that the signal power is equal to the noise power. So the signal power, or the total photocurrent, is equal to RP1, where P1 is the incident optical power. Photocurrent related to that is RP1. So this is the signal current, is equal to the noise current, and here is an expression for the noise current that we already mentioned. Then reorder this equation, move square root of the bandwidth to the left side. This actually represents the noise equivalent power. So this is the final expression for calculating the noise equivalent power. Its unit is going to be watt per hertz to the power of 1/2. Here is an example of calculating the noise equivalent power at 2 different bandwidths. At a bandwidth of, in fact, the noise equivalent power is given, and we have to find the optical power at 2 different bandwidths, at 1 GHz and at 10 GHz. So we know the equation for noise equivalent power equal to the incident optical power divided by square root of the bandwidth. We have to determine the incident optical power as a function of noise equivalent power and bandwidth. So move P1 to the left equal to NEP, noise equivalent power, times the square root of the bandwidth. Then put in this first value for the bandwidth, 1 gigahertz. The incident optical power requirement is 3.16 nanowatts. And if the bandwidth is 10 megahertz, then the requirement for the incident optical power is 31.6 nanowatts. So which one is better? This one is better, right? Because at 1 gigahertz, the power requirement is low, and that is what we want. Our photodetector should be able to operate at low input optical power levels as well. So which means that higher bandwidth is more desirable in photodetectors. Now, detectivity is the inverse of the noise equivalent power. We would like to have as small value of noise equivalent power as possible, which also means that it is desired to have high detectivity. It is a figure of merit of the photodetectors. Another terminology is the specific detectivity, which involves the photosensitive area as well. But we can deal with just this parameter. A high value of detectivity is desired in photodetectors. Here is a table showing different parameters for different kind of photodiodes: gallium phosphide based, silicon based, germanium based, and indium gallium arsenide based. The peak wavelengths are given, the dark currents are given for these photodetectors. The dark current actually corresponds to the leakage current under reverse bias, and this property is material dependent. It depends on the band gap of the semiconductor. If the band gap is higher, the leakage current generally is low. For example, the band gap of silicon is 1.1. The band gap of gallium phosphide is around 1.4. So wider band gap means it gives smaller leakage current, which is more desired. Similarly, if we compare silicon with germanium, silicon has a band gap of 1.1. Germanium has a band gap of 0.65, I would say. So since this has smaller band gap, it would have higher leakage current. And then if it is higher leakage current, then its required noise equivalent power would be higher as compared to silicon. And the required noise equivalent power of silicon would be higher as compared to gallium phosphide. And then since gallium phosphide has the lowest noise equivalent power, so it's going to have the highest specific detectivity for photodetectors. So it turns out that low dark current or low leakage current is more desired because it gives low noise equivalent power and higher detectivity for photodetectors. Here our goal is to calculate the short noise in photodetectors and the thermal noise in photodetectors, and then finally to calculate the signal to noise ratio of the photodetector. As we know that noise in a photodetector has three components: the dark current related noise, the photocurrent related noise, which can be combined into one equation, and then put in these values given in this example into this equation. The short noise in a photodetector turns out to be 1.79 nanoamps. Similarly, we have an expression for thermal noise as well. Put in these values into this expression, the thermal noise turns out to be 5.26 nanoamps. So it turned out that thermal noise is much bigger than the quantum noise in a photodetector. Finally, SNR is equal to the photocurrent square divided by the quantum current square plus thermal noise current square. So the signal to noise ratio comes out to be 7.26. Here we have another example. We consider an ideal photodiode, and the conditions for ideal photodiodes is that it's gonna have a dark current of 0 amps, and it should have a quantum efficiency of 100%. In reality, it does not exist, but for the sake of an example, we can assume an ideal photodiode having ID is equal to 0 and quantum efficiency of 100%. So we need to show that the minimal optical power required for an SNR is equal to 1 is P1 is equal to 2hc bandwidth divided by lambda. Now we know that at an SNR is equal to 1, our photocurrent is equal to the noise current. And we have an expression for the noise current, this one over here. So after further simplification, our photocurrent comes out to be equal to 2 times charge on electron times bandwidth. Now further we have to find this expression. So once again we know that our photocurrent is equal to our noise current. This is the photocurrent, IPH is equal to RPN, and this is the noise current. So after further rearranging, move R to the right, and then we also know in this expression that ID should be 0 for an ideal photodiode. Furthermore, IPH we already simplified, turned out to be equal to 2 times charge on electron times bandwidth. Replace all these values, and we finally get to this expression. Our input, our minimum incident optical power is equal to 2 times Planck's constant times the speed of light times bandwidth of the photodetector divided by wavelength of operation or wavelength of the incoming incident photons. Insert all the values, and the minimum optical power required for an SNR is equal to 1 for this example is 0.31 nanowatt. So this is the power corresponding to the noise power, or the minimum optical power required for the photodetector to operate. And then we can determine photocurrent as well. We already know the expression for that. Put in values, and our photocurrent is 0.32 nanoamps. And since we have an SNR is equal to 1, at this value we know that our noise current is equal to the photocurrent. So this turns out to be the quantum noise related current of the photodetector. That concludes the lecture slides, and here is your homework 4.1, 4.2, 4.3, 4.4 and 4.5. The physical constants are given at the end of the lecture. This concludes the lecture, and I will see you next time, inshallah.